Okay, good morning. So just before we get back into the lecture material, a couple of quick announcements. First, a reminder that on Thursday morning, we're going to write the second lecture quiz. So that is next class. That lecture quiz will be run in the exact same way as the first lecture quiz. So it'll start, or the email will be sent out at 8:15, and you will have until 9:20 to return your results via CrowdMark. The lecture quiz is on lecture sets number 4 and lecture set number 5. So it covers ANOVA, one-way ANOVA, multiple comparisons and contrasts. It has the same number of questions as the first quiz. So it's 3 questions. There are parts associated with them. And it is worth 29 marks. So the same number of marks as the first quiz. So in terms of structure, how it's going to be written, basically all of the details that surround the actual writing of the quiz, it'll be exactly the same as the first quiz. So that's the first announcement. I'll send out another reminder about that after class and tomorrow, just to make sure everyone's aware. And I'll lecture for the first about 15 minutes or so. The second announcement is that after the reading week, we will be, I guess not returning, but we will actually be starting officially the hybrid schedule that was originally proposed in the course outline, which means that we will have class in person and still have some online classes based off of the definition of the hybrid course. So I will send out reminders about that as well. But essentially, you should plan to be at the university for lecture the first Tuesday after reading week, and all in-person lectures cannot be recorded given the rules. So we will have a mix of in-person and online for the remainder of the semester, which is really only about a month. The online courses will be run, or the online classes will be run in the same way that we've had so far this semester. So those will be recorded, and I'll meet with you on Zoom like we usually have been. We'll just be mixing in-person classes and in-person testing, which will be nice to complete the semester. So I'll send out reminders about that as well, and I'll send out the schedule or the tentative schedule for that. Obviously, if it'll be flexible, so if things come up, we can adjust as needed. But the original proposed idea is in the course outline. So if you are interested in what that schedule is going to look like, you can review the course outline, and that'll explain sort of how I intended to run the hybrid, how I intended to run this course under the hybrid definition. And again, I'll send out reminders just basically reiterating that idea. All right, so returning to campus after reading week, and quiz 2 is on Thursday. So those are the 2 major announcements. With that being said, any questions? I don't think so. No, assignment 3 we already did. Assignment 4 is due on March 4th, which is the Friday after the reading week. Yeah, Madeline, that's a good question. So, so with regard to assignment number 2, what happened was the TA became ill, and the TA was hospitalized. So there's been just a delay, basically, given her recovery time. So I spoke with the TA at the beginning of the week, and the indication was that the marking should be started soon. So I'm hoping that both assignment 2 and 3 will be back quickly. I'll touch base with the TA again and see what's going on. But the solutions have been posted, so you do have those to use to study. And That's the most updated information I have at this point. If it continues to drag on, I'll talk to the other instructor, and we'll have to come up with some sort of plan to try and get it finished, basically. Any other questions? All right, so if there are no other questions, oh, and for quiz 2, again, there's practice problems also posted. So those cover the topics that are going to appear on the first quiz, or on the second quiz as well. Okay, so quiz 2 on Thursday is the most pertinent update. Okay, so we're going to get back into lecture set number 7 today. What we're going to cover to start the class is a review of interaction diagrams. So we're going to work through an exercise where we are diagnosing whether or not there are main effects and interaction effects based off of an interaction diagram for a simple experiment. And then we are going to look at the details of the two-way ANOVA procedure and work through a fairly large example where we run the different hypothesis tests associated with the two-way ANOVA procedure. And I believe that there is also a fairly large interaction diagram that's included. Yeah, there is. And we'll look at another example of an interaction diagram for a more complicated type of design. All right, so on slide 14, we have 6 interaction diagrams. What we're going to do here is use the interaction diagrams to determine if there's a main effect between factor A or factor B. And then we are also going to determine if there is an interaction effect. Okay, so the way that I'm going to do this is I'm going to make a little charting system down here. So this will be the first graph. Okay, so this is going to be main effect for A, main effect for B, and interaction effect. And this is plot 1. Okay, so basically what we're going to do here is we're going to look at the first diagram, and we're going to try to determine, if there's evidence or I guess we can say evidence or any suggestion that there might be a main effect for factor A, a main effect for factor B, and interaction effect. So starting with factor A, what we are going to do here, and I'll use red to indicate factor A, is we're going to look at the 2 levels of factor A. So there's A1 and A2. So these are the 2 levels of factor A. So now what we're going to do is we're going to estimate what the mean is at each of these levels. So the mean of factor A is going to be the average of its 2 stacked points, or sorry, the mean of A1 is going to be the average of those 2 stacked points. And the mean of A2 is going to be the average of its 2 stacked points. So you can see here that for A1 and A2, the average is the same. So it's, in this case, it's a value of 35 because this is a very simple illustration. But the point is, just from a visual assessment, you can see that the 2 dashed marks for the mean of A1 and the mean of A2, they are the same value. Okay, so that would indicate here that there is no main effect. So means are the same. And that's essentially what we're how we're going to diagnose these going throughout. If the means of the levels are equivalent, there's no main effect. If they are different, then there could be a main effect. So now what we'll do is we'll look at factor B. same idea. So this time I'll use blue to indicate factor B. The levels of factor B run across the line segments. So the dashed line segment represents B2 and the whole or the filled outline represents B1. Okay, so the mean of B1 and B2 are going to be the averages on the line segment. Okay, so for B1, our average value is here. And for B2, our average value is here, right? Now, in this particular case, you can see that all of B1 is a value of 40 and all of B2 is a value of 30. So the mean is going to be 40 for B1 and 30 for B2. So we can say here that there would be evidence since means are different, right? Okay, and then the last effect is interaction. Interaction is very easy to diagnose. It's basically, are the lines parallel or are they not parallel? In this case, it's two parallel line segments. So here we would say no due to parallel lines. All right. Okay, so that's the gist of it for interaction diagnosis. So now we'll move on to the second graph. All right. So in the second graph, we have the same goal. Okay, so we start with factor A. So there are two line segments that are sitting on top of each other in this particular experiment. So B1 and B2 run across the exact same, or have the exact same value. So A1 is at 30, because if you average 30, like 30 plus 30 over 2 is still 30. And A2 is at what looks like about 40. So you can see here that A1's mean and A2, they are different in this case. So that would mean here that there's evidence of a main effect for factor A. All right, for factor B, the line segments are equivalent and they sit right on top of each other, which means that they have the exact same values at both levels of A. So in this case, since they are equivalent, this would mean a no. And because the lines sit on top of each other, they are also parallel. So this would be a no as well. All right, we'll do one more and then I'll stop for questions. Okay, so in number 3, starting with A, so for A1, the mean is about here. And for A2, the mean is going to be roughly here. So you can see that those are different quantities. So we have a main effect for A. Okay, so for B, we have the average of B1, we have the average of B2. Those are also different quantities now. So that would indicate a main effect for B. And then we can also see that the line segments are not parallel here. They're not perpendicular, but they're certainly not parallel. So we would say yes, or sorry. Yes, we have evidence of a main effect for the interaction. Okay, any questions? Okay. All right. Number 4. A4 is an interesting one. So here is A1's mean. Here is A2's mean. So those are at the same point. All right. Here is B1's mean, and B2's mean is also at the exact same point. But these lines are certainly not parallel. They're actually almost perpendicular to each other. So that would indicate interaction. Right. Okay, number 5. Okay, so here is A1's mean. Here is A2's mean. So those are at the same value. Here is the mean for B2. Here is the mean for B1. So those are at different values. And then those lines, again, those are not parallel. So that would indicate interaction. Okay, and then in the last system, you can see everything is equivalent here. So this would be a fully non-interacting, no main effect system. Okay. And that's essentially how we can use an interaction diagram to diagnose whether or not there's presence of a main effect or an interaction effect. Any questions? All right, so if there are no questions, we'll move on to talking about the details of the two-way ANOVA. Just before we get to that, a couple of quick points just highlighting what we had just gone through on the previous slide. So interaction diagrams can be used to assess whether or not main effects or an interaction effect are present within an experiment. Main effects represent differences between the levels of one factor, and the interaction effect represents whether or not the levels of the two factors are creating a change in the mean response. In general, when assessing the diagrams, interaction effect is very easy to check for. Essentially, if the lines are not parallel, there could be an interaction effect. Checking for main effects is a little bit trickier. You have to basically compare the means of the different portions of the levels to one another, or rather you have to compare the means of the levels to one another. The interaction diagram is meant to be a preliminary check of the system before we run the two-way ANOVA. So assessing the interaction diagram cannot give us statistical evidence for a main effect, which again is just a difference among the levels of one of the factors, or for the interaction effect. That's where our two-way ANOVA procedure will actually come into play. So just like with the one-way ANOVA or the ANOVA for the completely randomized block design, we're using F-tests to determine if there are differences among the means across either the factors or the interaction or the treatment combinations in the case of the interaction. And that's going to be done in a very similar way to what we saw before. But the diagram can be used beforehand to pre-assess the system. Okay, for a two-way ANOVA, our data, we actually saw an example of this already, but essentially the way the data is laid out is you have your two factors creating a rectangular or a square grid. And then at each level of the factor, you have replication. So the little r, which is shown here, counts the number of replications that are occurring at each treatment combination. So in the two-way ANOVA, kind of like with the CRBD, you'll have some level of factor B, some level of factor A. Those levels will combine, and then you'll replicate observations at that treatment combination. With the CRBD, you have a treatment and a block that combine, but you only have one value at that particular combination. I think there is a design where you can also replicate in a block situation, but we're not going to study that in this particular class. Okay, so sort of like with the other designs, we're basically going to have means for all of the different situations. For example, we can have a mean for B1 or a mean for each level of factor B. We can have a mean for each level of factor A. We'll have an overall mean. And then we call, for each of the sets of replications, we have a treatment combination mean, which is shown here. Okay, so for example, if we were to consider this set of values here, this is going to have its own mean, which would be X bar AB11. Okay. So X bar AB11 represents the mean of the replications at level 1 of factor A and level 1 of factor B. And for every set of replications, you can compute a mean, and that's what this X bar AB represents. Okay, so really a fairly natural extension from the CRBD in the sense that you're now just saying, okay, instead of having a block that's confounding, let it be a factor that I want to investigate. I'm going to start computing the means at that factor. I'm going to consider the means of all the combinations. And now I have a system composed of A-B interaction overall 4 means, as opposed to a system composed of 2 means or a system composed of 3 means, for example. So when we're using a two-way ANOVA, sort of like with the one-way ANOVA and the CRBD, we're essentially saying, let all of the data in our experiment be normally distributed. So we add on that normally distributed error at the end, right? So this thing here is normally distributed error, right? And essentially we're just the system is just becoming more complex. So now we're saying, okay, we have normally distributed values. The mean of those values is going to be some overall mean mu plus some treatment effect from factor A plus a treatment effect from factor B plus a treatment combination effect that we call AB, right? So in this situation, given the original model, we're basically just saying X, I, J, K is now normal mu plus alpha I plus beta J plus alpha beta I J sigma squared. So effectively, the assumptions for the two-way ANOVA are going to be very similar to the assumptions that we had for the CRBD and the assumptions we had for one-way ANOVA. In particular, we're going to assume all of the observations are normally distributed. And again, we're going to assume that across all those treatment combinations, the variance of all these values is the same as well. Or in general, all of the observations are normal and they all come from a normal distribution with the same variance. In addition to that, we also have the independent samples assumption. So basically within each treatment combination, you can assume independence, and all of the data that was collected was done so via a simple random sampling process. So there's no dependence between any of the observations in the data set. All right, so we have the same set of assumptions that we've seen for all of the ANOVA experiments. We have a slightly more complicated model because we are now investigating interaction effect. We know that what we're going to build towards here is an ANOVA table where we can assess the system. That ANOVA table is going to be based off of a decomposition of the sum of squares. And that decomposition is shown here. And you can see again, all we're doing in this situation is basically pulling more information out of that error term. So we still have SST, and it's very important to consider here that this is same value given for one way ANOVA and the CRBD. And essentially the point is there's only one way to measure total variation in a data set. You have your response and you take the difference between each value and its mean. That's the only way to do it. And you square that and you add them all together. So this SST value for all of the different ANOVAs that we will consider is calculated in the exact same way. It's basically just the numerator for the variance of the total difference of every observation and the overall mean. What we have progressively seen from lecture set 4 to now lecture set number 7 is the way that we decompose that variance changes depending on the design that we are considering. When we considered only the one-way ANOVA, we had SST equals SSTR plus SSE, a representation of a much simpler time. When we had the CRBD, we said, okay, we have SST, we have SSTR. From the error, let's pull some information out and we're going to call that a block. So now we have SST equals SSTR plus SSB plus SSE. Now what we have is here's our total sum of square SST. We're going to say from that total, we're going to have an SSA term, an SSB term, SSAB term, and this error term again. So we've just pulled additional information out of the total so that we can investigate this particular system that includes the interaction. All right, so it follows that we're going to have a larger ANOVA table for the two-way factorial design. So an example, or the general two-way ANOVA table is shown on slide 21. As you might expect, you can see that we now have additional sources on the table. So we have factor A source, we have factor B source, we have our interaction, we have an error, and then we have a total. Okay. All right, so for each of them, we have a degree of freedom. Those are still additive. So all the degrees of freedom sum to DF total. We have the individual sum of squares. All of the sum of squares sum to the SS total. Then we have the mean squares. Just like before, we don't really need the mean square total. We only need mean square A, B, mean square A, B, and the error. And then we have the F statistics for each of the main effects and the interaction effect. So there are actually 4 different tests that fall out of a two-way ANOVA table. 3 of those tests are what you would expect. So we have a test for interaction, and then we have a test for each of the individual main effects, right? So that follows the table. If we look at the table design, it's like, okay, we have a test for factor A difference. We have a test for a difference among the levels of factor B. And we have a test for the difference among the treatment combinations, which would be the interaction effect. All of these are F tests, and all of these are run in the normal way. So 6-step procedure, where we use the F value, and then we can either take a critical value approach or a p-value approach based off the degrees of freedom of the particular factor, and make a conclusion about whether or not there's evidence of a main effect or an interaction effect. The other test or the fourth test that we can run is called a model utility test. The model utility test is sort of another type of pre-test that you use to validate the system before you go through and run each of the individual tests. So for example, if we had an interaction diagram, the interaction diagram showed nothing. So if it was just two flat lines, you might argue that running the ANOVA is pointless because you're not going to see any differences. But you might be asked, okay, run it anyways, just to determine that this is true so we can statistically say there's no differences. You could theoretically run this model utility test first, which basically would pre-check the whole system. And if the utility test gives no evidence of a treatment effect, this would basically say that there's no there's no differences among the means of the treatment combinations, and there's no differences among the means of each of the main effects. Right. So this particular test is again just an F test where we are summing each of the sum of squares for the main effects and interaction effects together, and dividing by the degree of freedom for the main effects and the interaction effect. And then we are comparing this F statistic shown in 2 to an F distribution where the numerator degree of freedom is AB minus 1 and the denominator degree of freedom is N minus AB. So we have, again, 4 tests: the utility test, main effects test, and the interaction effect test. So when we're actually testing a system or when we are using a two-way ANOVA to test a system of means, the recommended procedure is to do the model utility test first. If you reject the null hypothesis in the model utility test, then we would run a test of the treatment effect or the interaction effect. So we would go model utility test. If that shows rejection, test for an interaction effect. After we test for the interaction effect, then we would test each of the main effects. Okay, so that's the suggested order: model utility, interaction, and then each main effect. And it doesn't matter what order you do the main effects in. And then, again, just the logic here is you're going from most complex test to least complex test. So test of the entire system, test of combinations of the main effects, and then test of each main effect separately. That's the logic. Okay, so now we can actually look at an exercise to highlight all of these different tests and reevaluate our original experiment, and to evaluate the original data set that we used at the start of class. All right, so the motivating example for the two-way ANOVA procedure is the iron-biron experiment. In the iron-biron experiment, we were testing to see if the club choice and the brand of a golf ball made a difference in how far a golf ball travels on average. So if we go back just very quickly here to slide 4 or slide 3, this is the data set that we are using for this particular experiment. Okay, so we have factor 1, which is the club. We have factor 2, or actually, I guess I wrote it differently. Well, we have a brand factor. We have a club factor. For the brand, we have 4 levels. For the club, we have 2 levels. And then we have 4 replications at each of the treatment combinations. So for each golf ball brand, there's 8 observations. For each club, there are 16 observations. And in total, we have 32 observations in this system. Okay. Okay, so we're going to basically run through the evaluation of this system in order of the ideas that we have discussed so far. So we'll start by evaluating the interaction diagrams. And then what we will do is we will look at the model utility test. Then we will look at the interaction test, and then we will do the main effects test. Okay. And we're going to assume for illustrative purposes that the assumptions are intact as we move through this experiment. Okay, so in our two-way ANOVA table, we have brand effect. So that's the golf ball brand. Then we have the club effect. Then we have the brand club interaction effect. Then we have an error, our error source, and then we have our total. Okay, you can see that we have the DF and the sum of squares for all 5 sources. I've only computed mean squares for brand through error and F statistics for brand through error. Okay. Okay, so I'm actually going to do this part first. I'm going to make a little note here. Future. And then these parts here, so A through C, this is the testing protocol. Okay, so parts A through C are basically just breaking down that testing protocol into 3 different questions: utility test, interaction, difference. Okay, so let's start by looking at this interaction diagram, which is composed here, which is shown here. Okay, so we have golf ball brand on the x-axis. Each of the circle or each of the dots or open face circles on the diagram represent a mean for the replications at each of the treatment combinations. On slide 27, I actually show a table of the means, right? So for example, the dashed line is a 5-iron and golf ball brand A. So A and 5-iron give a mean of 171.3. So this value here is 171.3. Whereas this value here is going to be 228.425. And then it would be a similar thing throughout the system. So for example, here we would have 182.675, and then etc. for the rest of the system, okay? So we can evaluate this system in a pretty similar way to how we evaluated the original system. So we're going to have main effects for the brand. Or I guess I'll move this down here. We'll have main effects for the club, and then we'll have interaction effect. Okay, so for we'll start with, let's do club first. Club is actually very easy. So we have 2 clubs, driver and 5-iron. So for the main effect for club, essentially what we're doing is we're comparing the mean of the driver to the mean of the 5-iron. So we can see from our table of means that the mean for the driver is 233.75. Okay, so that's going to be right about here, just a little bit higher. This is 233.75. Okay, so that's the mean for the driver. And then you can see the mean for the 5-iron is 170.42. Okay, so that's going to be basically right down the middle here. Okay, and then going back to what we originally discussed, the idea is these two values are not the same. So that would indicate a main effect for the club type. So because the driver average distance and the club average distance are different, this would basically say, yes, we have a main effect for club type. Right? And that follows directly from what we were talking about before when I was just marking those dashed lines. It's just a difference in means among the levels of that particular factor. Right? I'll do the brand in green. Okay, so for the brand, it's actually the same idea. You can see that the means are a lot closer here now. But basically, we have for brand A, a mean of 199. So that's going to be right about here. So that's going to be A, or I'll write this as X bar A. And then B is going to be 208. So that's right about here. So that's X bar B. Sorry, and for clarity, this would be X bar driver. This would be X bar 5-iron. Okay, C is at 205. So that's right about here. And D is at 195. So that's going to be right about here. All right, so these means are much closer together, but again, they're not at the same points. So given that they are not equal, that would suggest that there could be a main effect. So we would have to say yes here based off the interaction diagram. But again, given how close these values are to one another, there might not actually be statistical evidence of a difference. And that's why we still need to check the system with an ANOVA. For the golf ball club or for the club type, it should be, given how drastically different those values are, it would be pretty surprising if there wasn't a difference, but we still need to validate it using statistical evidence. All right, so the last effect type would be the interaction effect. So basically here, the way that I do this is I look at the system in segments. So let's say we look at A to B segment for the driver and the 5-iron. Okay, so so maybe we can do something like this. Okay, so this black line is just breaking the diagram up into segments. Okay, so I'm just considering each portion separately. Okay, so if we look at the segment for A to B, you can see that the lines are kind of heading in this direction. So they're converging on each other as they move from A to B. So that is not parallel. So that would be the first evidence of a bit of interaction. When we look at B to C, we can see that the lines are diverging from each other. So again, not parallel, evidence of an interaction. And then as we move from C to D, those look slightly more parallel. They're heading in the same direction. So maybe that would not indicate evidence, but overall, based off of the change from B to C, we would have to say that there is presence of an interaction here because we do not have a system of parallel lines. That's what it boils down to. Any questions? All right, so comparison. Okay. All right, so what we'll do now is we'll start to work through that testing protocol. So this here, just for clarity, this would be the answer to part D, which we did first. Okay. Okay, so now we're going to do part A. Does the model utility test give evidence that the interaction and main effect should be tested? So we're going to do the model utility test now. Okay, so this is going to be part A. So we have step 1. So we have H0, no evidence of treatment effects. Versus HA, evidence of treatment effect. Okay, and then on step 2, we have alpha equals 0.05. Okay, so then on step 3, we have F is equal to MSTR divided by MSE. So this is going to be from the ANOVA table. Okay, well, I'll just write it out. So this is going to be SSA plus SSB plus SSAB divided by DFA plus DFB plus DFAB. And then this whole thing is going to be over the MSE. Okay, so I'm going to pull the values out of the ANOVA table. So I'm just going to be using the values that are shown here on slide 25 to complete the F statistic. So we have 801 plus 32093 plus 766, and that's going to be divided by, so from the table we have 3 plus 1 plus 3. And that's going to be over 34. Okay, so that gives us 4,808.571 divided by 34, which is equal to 141.4286. Okay. So that's the F statistic for the model utility test. Okay, so then on step 4, we can take critical value approach or the p-value approach. Right? I will show So I'll give the illustrations here for the first test, just for practice purposes. And then for the remaining tests, I'll just give you the critical values and the p-values just for time's sake. So starting here, if we were to take the critical value approach, okay, so we're going to sketch our F curve. Okay, so we're going to have an F value at 0.05. And then the degrees of freedom for this test is going to be the sum of the degree of freedom is going to be the sum of the degrees of freedom that we used in the F statistic. So the DFA plus DFB plus DFAB. So that's going to be 7. And then we're going to have the degree of freedom for the error term, which is 24 from the ANOVA table. Okay, so that's our critical region. So now we have to look up this value. So 724. So we need to get our F table here. Maybe 3 again. 7. Nope. 5. Okay, so here's 7. Here's 24, 0.05, 1, 2, 3, 4, 5, 6, 7. And that gives us 2.42. Okay, so the critical value for this test is an F value 2.42. All right, and then our test statistic is 141.4286. All right, so obviously we're going to reject in this case. Okay. So then if we take the p-value approach, okay, so this is going to be our F value 141.4286. Okay, that little green part there is going to be the p-value. So in this situation, the p-value is equal to the probability F is greater than 141.4286. Okay, so we go back to our F table. We have, so we have the same degree of freedom, so 7 and 24. Okay, so we're working with this column of numbers here. Okay. And you can see it's very clear, right? The F statistic is huge. So the 141.4286 is much larger than the 3.99. So that means that the p-value in this situation is going to be smaller than 0.005. And the truth is, given the magnitude of the F statistic, so given how big that F statistic is, the p-value is going to be essentially zero anyway, All right, so we can say, since the probability F is greater than 141.4286 is less than 0.005, then the p-value is less than 0.005. Okay, so regardless of which approach we take, we can reject H0. And then we can say at the 5% significance level, the data provide sufficient evidence to suggest that there is a treatment effect. So we have at the 5% significance level, the data provides sufficient evidence to suggest that there is a treatment effect. Right, any questions? Okay, so in part B, we're going to test the interaction effect. So same thing here. So we're going to have H0, no evidence of an interaction effect versus HA, evidence of interaction effect. Okay, and then on step 2, we'll have alpha equals 0.05. And then on step 3, so all we have to do here is pull the values out of the ANOVA table. So for the interaction, the F statistic is 7.452. So we have F equals 7.452. Okay. So on step 4, if we take the critical value, we're going to have an F on 0.05. The degree of freedom for the interaction term was 3. So this is an F on 0.05, 3, and 24. Okay, so that's going to be 3.01. Right, so 3, 24, 0.05, 3.01. Okay, if we take the p-value, here, so if we go to our F table, same degree of freedom. So our F statistic is 7.7 or 7.452. So that's larger than the largest listed value. So that means that the p-value is going to be less than 0.005. Right. So then on step 5, we will reject H0. And then on step 6, we can say at the 5% significance level, the data provide sufficient evidence to suggest that there is an interaction effect. Okay, and then in part C, we have to do each of the main effects, right? So we have a main effect for the golf ball brand. We have a main effect for the golf club. It doesn't matter what order you do the main effects in. You can follow the table or you can do it in reverse. It doesn't make a difference. So I'll just follow the table order. So we'll start with the brand. Okay, so for the golf ball brand, we're going to have H naught alpha A equals alpha B equals alpha C equals alpha D. Versus the alternative that there's a difference in the system. So we can say HA, not all brand means are equal. Okay, and then on step 2, we have alpha equals 0.05. And then on step 3, from the F table, the F statistic for brand was 7.791. Right. Okay, so then on step 4, if we take the critical value approach, we have an F on 0.05, 3, and 24. So we actually have the same value that we had above. And we can show that given our previous, given the test for interaction, it's going to be the same p-value as well. Okay, so then on step 5, we can reject H0. And on step 6, we will have at the 5% significance, the data provide sufficient evidence to suggest that there is a difference in mean distance traveled by each golf ball brand. All right, and then for the club, I'm gonna just be a little bit lazy here. It's a very similar test. So I'm just gonna copy and paste and edit a couple of things. Okay, so for club, okay, so for the club type, we're gonna have the distance for the 5 iron is equal to the club effect for the driver. So we would have not all club means are equal. The F statistic here is 936.752. The critical value for this test is going to be an F value on 0.05, 1, and 24. Okay, so that's shown here. 1, 24, 0.05. So that's 4.26. So obviously the p-value is going to be less than 0.005. The F statistic is massive. Like that p-value is going to be basically 0. And then we're going to reject, and then we can say at the 5% significance level, the data provides sufficient evidence to suggest that there is a difference in mean distance traveled by the struck by each club. Okay. And that is a two-way ANOVA testing system. Ugh, it's long. Any questions? Is there a way to check off the tests we need to do? If I'm understanding the question correctly, there is, so on slide 24, I outlined the testing procedure. So test 1 is model utility test. Test 2 is interaction test, and test 3 would be the main effects test. So it would go utility, interaction, main effect 1, main effect 2 would be the order. Any other questions? Okay, so once we run all of the utility, once we run our testing procedure, depending on which hypotheses we reject, we would then have to run the multiple comparisons. So in our situation, we had interaction effect and then the 2 main effects, all of them resulted in rejection. So we're going to be running multiple comparisons for the interactions, so the treatment combinations, for the club and for the brand. Okay, So what we're going to do on this slide is basically go through the multiple comparison process, focusing on how to compute the margin of error for each of those different multiple comparisons. Once you have the margin of error, the rest of the procedure is exactly the same as it was before. So you take the difference in the means and you compare the mean to the margin of error to see where the differences lie. So we'll start with the club effect as our first illustration. Okay, so the first thing we're going to do is, well, I'll try and be very strict and follow exactly the protocol that we laid out before. So we would have okay, so this is going to be consistent, but we'd start with, okay, so 1 alpha E is equal to 0.05. And then we would have 2 little m is equal to k choose 2, okay? So for the club effect, k is going to be the number of clubs that we considered in this experiment. So this is going to be 2 choose 2, which is equal to 1. Okay. 3 is going to be alpha I is equal to alpha E over 2 times m. So this is going to be 0.05 over 2, which is 0.025. Okay, and then on step 4, we would put the means in ascending order. Okay, what the hell? I'll do it just for completeness sake. There's only 2 club means. So we have 170.4125 to 233.75. Okay, and then just for reference, if you're not sure, see table on slide 27. Okay, and then the main part here. So now what we're going to do is compute the margin of error for this comparison. All right, so what we're going to have here is capital E is equal to a t-value on alpha I, comma, DFE. And this is going to be multiplied by the mean squared error, 1 over the sample size for the 5-iron plus 1 over the sample size for the driver. Okay. So this is going to be a t-value on 0.02524 multiplied by 34. Okay. And then going back to the original table of our data set, each club had 16 observations associated with it. So this is going to be 1 over 16 plus 1 over 16. All right. Okay, so we need our t-value on 0.025 and 24. So that's 2.064. Okay, which is multiplied by 34, 1/16 plus 1/16, which is equal to 4.25. All right. Okay, and then basically what we would do is we would just take the difference between the two clubs, and then we would compare that to the margin of error. But you can see, like, basically the difference between the clubs is in the area of 63. So 63 is much bigger than the margin of error. So we would have evidence of a difference here. We also know this is true because there's only 1 degree of freedom for the club effect. So the ANOVA table is basically telling us that there's a difference between the clubs directly. Okay, I'll do one more just to try and get through this. So we're going to do the brand now. So this is going to be very similar process. Alpha E is 0.05. Little m is K choose 2, which is now going to be 4 choose 2, which is 6. Okay. 3. So alpha I is going to be alpha E over 2m, which is going to be 0.05 divided by 12, which is 0.0083. Okay, and then we would have to put the means in ascending order again. So this time there's going to be 4 means, 1 for each brand type. So we would have 195.125, 199.8625, 205.1375, and then 208.2. Okay. Mind you, if you're asked to compute margin of error, you don't need to go through the mean assorting step. I'm just doing it for consistency with the directions from lecture set 5. Okay, so then we're going to have T, I, DFE multiplied by the square root of the MSE. So this is going to be 1 over N. I'll call this brand I plus 1 over N brand J. Okay, all of the golf ball brands have the exact same sample size. So we only have to do the margin of error calculation once. Each golf ball brand has 8 balls associated with it. Okay, so this is going to be equal to T on 0.008324 multiplied by the square root of 34, 1 over 8 plus 1 over 8. Okay, so we will approximate T 0.008324 with T 0.00524, because that's the closest we can get using our T table. Okay, so that gives us 2.797. So here we're going to have 2.797 multiplied by the square root of 34, 1 over 8 plus 1 over 8. And that gives us 8.382. Okay, so obviously I'm out of time. I'll stop here for today. On Thursday morning, I'll lecture for the first 15 minutes. Hopefully I'll finish up this lecture set, and then we'll have the quiz, and then we have reading week, and then we'll meet in person for the first time in this semester. Okay, so have a good couple of days. Let me know if you have any questions. I have office hours tomorrow. Stay tuned for the announcements regarding the quiz reminder and class structure. And Yeah, have a good one, and I'll chat with you guys later.